Our first section is going to go into some details about the background of thermal theory to help you best select which materials to use for your application.
All right, thermal theory refresher. Basically, the point of this slide is talking about how thermal interface materials are meant to serve in the interface between a heat generating component and a cold plate or a cooling feature. And then they're meant to be better than air solutions because air is a good insulator. Throughout this presentation, you will hear us refer to thermal interface materials as TIMs, as they're often referred to. Thermal interface materials are just that, materials meant to transfer heat at the interface between a heat generating component and a cooling feature. Heat generating components can be anything from semiconductors or batteries to large electronic assemblies, while heat sinks or housings or enclosures can serve as cooling features.
TIMs use conduction to pull heat away, relying on contact between components to remove interstitial air gaps. Densely packed ceramic particles within silicone binders give TIMs excellent durability and thermal conductivity while ensuring electrical insulation and no concern of shorting electrical leads.
Thermal conductivity and thermal impedance are two properties that are most commonly used to describe the performance of thermal interface materials. Thermal conductivity is a bulk material property, and it's used to compare the ability of a material to transfer heat. It's also most commonly used to compare across competitive materials. Callie, how's that different from thermal impedance?
Thermal impedance is different in that it's the real-world property that demonstrates material performance based on part thickness and application-specific pressure. The thermal impedance takes into account the important factor of thermal contact resistance, which is the decrease of thermal transferability at the interface between the TIM and the heat-generating component.
Across all industries and nearly all applications, we see pretty common drivers for the use of thermal interface materials. As boards get hotter and enclosures get smaller, higher performance density and greater ease of application drive continuous improvement. Callie, of the properties on this slide, have you seen specific drivers influence customer decisions?
Certainly. So typically customers come in and they want the best performing or the highest thermal conductivity material, which correlates to the lowest thermal impedance material. But just going for the best thermal material doesn't always meet their application needs. So there are other physical and regulatory properties to discuss when deciding on a thermal interface material. For instance, having the greatest conformability in a product is highly desirable since that helps wet out on each surface and really drive the thermal performance of the material. And also it's really important to determine how the material is going to be applied in final manufacturing processes. For instance, whether the customer wants to have the material manually assembled onto a part or through automation.
So, what can we do for you?